Hey there, guys. Welcome to this chemistry notes video. Um, so this video is going to be covering the chemistry unit 1.3 notes, covering lab equipment and metric measurements. Okay. So yesterday we were going over, how on different techniques and strategies, proper usage of lab equipment, kind of looking at different lab equipment, sketching down what they look like, et cetera, et cetera. So here, just getting right into it, here is a whole big old list of here's a big old list of lab equipment that for the most part most chem classes, if not all chem classes, use, or at the very least mention. And you can go through these yourselves. I'm going to have an assignment for you guys, or at least I planned on it. Maybe I won't. We'll see. But here's a list of all these materials. Now, a lot of these you've already come in contact with. So like goggles, safety glasses, graduated cylinder, pipette, spatulas, scupulas, all that good stuff, test tubes. You should have some experience with. But it's possible that there's some in here that you haven't had experience with. So maybe evaporating dish, maybe we haven't used one of those before. It's possible we haven't used a Bunsen burner before. Maybe we haven't used a reaction tray, whatever it may be. So or a crucible. There's possible there's some things in here we haven't used before, or at least not really terribly used as in the way that you would normally use them in a chemistry lab. But anyway, there's the list for you to take a look at. Do you need to memorize this? No, you just need to be familiar with that and understand that these are, tools that we'll be using at some point in our chemistry labs here at the school. Okay. And I have you guys walk around. Yeah, usually that was the beginning of the year kind of thing. And obviously this year, not so lucky on that. Okay, so getting right into units of measurement. So remember, units of measurement that we follow, it's at least in the scientific community, in the scientific world. Man, I hate that word community, but in the scientific world, in practice, we use the SI units. We use the metric system, and these are a system of units that are streamlined in order and are used by scientists around the world, so that you don't have language barriers. So it's easy to convert. So it's easy to understand. You've got clear, concise units, all that good stuff. And so in the SI units, we have these things called base units. And base units are more or less the units we use for a particular kind of measurement. And there are seven metric units. So we measure things by their mass, their length, time, their count, their quantity, temperature, electric current, and luminous intensity. Okay. And these are the base things, the base units, the base kinds of measurements that we use. There's almost think of it like your senses. Like you've got touch, you've got smell, you've got hearing. Mass, length, time, count, temperature, all that good stuff is kind of on that same idea. And each of them have their own specific particular unit of measurement. Now you're probably looking at mass and saying like, well, Mr. Sheeline, I thought mass was measured in grams. It is measured in grams. It's the distinction here is that the kilogram is the specific kind of measurement that we derive our other measurements from. So a quick little history on that, and it's super quick, super broad, and may not really cover most of the details. But for the most part, the kilogram is based off a measurement of a particular substance. Right now, I believe it's silicon. There is also one that's made of, I think it's magnesium, but locked away in a vault. And I think right now it's the UK. There is the literal gold standard of the kilogram. Not literally that it's made of gold, sorry, but it's a literal standard. There is an actual object that we are using to base all the gram measurements from, and it's this big old hunk of metal sitting in a vacuum chamber, sitting in a double locked vault that scientists use as a reference point. And I can't remember the particular metal, but it's a very, very low reactive metal. It's one that doesn't its isotope doesn't change hardly ever, so it's a very, very stable element in material that will pretty much remain constant at exactly 1 kilogram for, I think it's another 200 years or something like that. But anyway, so the reason why it's a kilogram and not just a normal gram is just because that's the reference point, is that a kilogram is our reference. Whereas, for length, it's a meter. For time, the base unit is second. Count quantity is a mole. And we get into moles later on down the road. But for the most part, we use moles for the quantity of, it's the quantity of a particular amount of an element, of a molecule, based upon what's called Avogadro's number, which again we get into later on down the road. Temperature is just Kelvin. It's just the metric unit of temperature. Forget Celsius, forget Fahrenheit, because Kelvin has a higher range, and both in the negative and also the positive, and could be just used to measure a whole lot more. Celsius and Fahrenheit are much more for like human conditions. What's the immediate temperature of your given environment? How hot is this thing? How cold is this thing immediately in your environment? Unlike Kelvin, where Kelvin is like, well, what's the temperature of Pluto? What's the temperature of Mercury? Okay, an idea being, or what's the temperature of the surface of the sun, right? And the idea being is that there's a much wider range of measurements within Kelvin than there are Celsius and Fahrenheit, because for Fahrenheit, it's some crazy number of like 1,000,000 degrees. Kelvin, I don't remember what it is exactly for Kelvin. You can Google it real quick. But for Kelvin, it's some 100 degrees or something like that in Kelvin. I'd have to double check. It's been a while. But idea being, it's a higher range. You have ampere for electrical current, and then you have the candela for luminous intensity. We usually use lumens, which is a derived unit from candela. But anyway, so then I mentioned it. So what are derived units? So these are calculated units made from combinations of base units. So area, and those are supposed to be, I'll just make a change on these. If you notice, these are supposed to be subs or superscript. So that's my bad. So like this, so all of this stuff right here, it should actually, like all of this, it should look like this. It should be M2 or M squared, F2 squared, CM squared. That's what they're supposed to look like. So I'll go back and I'll change those just so those notes look correct. So my bad on that. But that's, M squared. And again, just don't confuse yourself, and make a note that, maybe even go off to the side, make a note that, that should be right here. This should be, here, hold on. So that should be meters squared, feet squared, centimeters squared, inches cubed, centimeters cubed, feet cubed, meters cubed, grams per centimeters cubed. Okay. Yeah, that's my bad there, guys. I'll make those changes. Okay. But these are derived units. So notice the meters squared. Remember, area is length times width, and so you can just say area is just m squared. Volume is your meter cubed. It's centimeters cubed. These are derived units from the base unit that we use, right? Because a base unit is just a single measurement of that single unit. So 1 meter is the base unit. Meter squared is a derived unit. Okay, and then it should be pretty obvious. It's just combining and altering your base unit is pretty much all it is. And then you have your metric prefixes. So we should be quite familiar with these now. We'll get into this a little bit more when we get into dimensional analysis later, in the year. But just for right now, just remember metric prefixes. These are those prefixes that we place in front of metric units, indicating a particular range of values. And remember, these prefixes move within units of 10. So for the most part, you just have to move your decimal to the right or the left, depending if you're increasing your range or decreasing your range. Okay. So the smaller to larger prefix, you move your decimal to the left. Larger to smaller prefix, you're moving your decimal to the right. And that's pretty much what you need to know for the test coming up. There won't be a whole lot talking about metric prefixes. This is more of a reminder, hey, these exist, and we're going to get into them later on down the road. So be prepared for metric, using metric prefixes for, say, dimensional analysis. And then we have uncertainty in measurement. So, and again, these are things we're going to continually go back and forth into as we go, throughout, as we continue down the road here this year. But exact number versus inexact number. So the best way you can think about these things is just trying to remember their definitions. in their examples. So an exact number, these are numbers whose values are known exactly with no uncertainty in the amount. So these are constants. These are conversion factors. So for instance, a constant would be the speed of light. The speed of light will always be the speed of light. It is an exact number. There is no ifs, ands, or buts about it. We do not derive a significant figure from these numbers, and that's where it really comes in, is understanding sig figs, significant figures, which again we'll get into that down the road. This is just saying, hey, these exist for right now, and at least know the definitions of them. And so exact numbers, again, they're your constants, they're your conversion factors. So for, as another example, so a conversion factor, there's always 1,000 meters in a kilometer. Okay, that does not change. And we do not derive our significant figures from the sig figs in our conversion factor, the 1,000 meters to 1 kilometer. We don't do that. Okay. But then we have our inexact numbers. And these are the numbers with, obviously, uncertainty. And for the most part, these are the measurements you're going to make. So if you're measuring something off of a quad balance beam, that whatever number you come up with is definitely not an exact number. That is an inexact number. Okay, it has a whole lot of uncertainty to it, because it's idea being, well, do you just stop with the 1 decimal point, or is there an unlimited or infinite amount of decimal points that you can't measure with the simple scale that you're using? So again, easiest way to remember, inexact numbers are your measurements, exact numbers are your constants. Okay. All right, scientific notation. So scientific notation is a way to write very large or very small numbers much more easily. So here's some steps, and we're going to go through these examples here. Here's steps of how to put numbers in correct scientific notation. So your beginning number has to be between 1 and 10. So meaning you can't, when we're writing correctly in scientific notation, it has to be between 1, and it really should be like, it should be 1 and 9.999, like infinitely repeating is what it really should be. It's just tons easier to say. So it's supposed to say this, is that your number is supposed to look like this. It's supposed to be like 1.249. It's supposed to be 3.62, right? It's not supposed to be like this. It's not supposed to be 36.2. Okay, it's not supposed to be 12.49. Because notice 36 is not between 1 and 10. 12 is not between 1 and 10. And even this, we can't do this. We can't do 10.20. No, we can't do that. It has to be this. It has to be 1.020. Okay. It has to be this way. We cannot do this. Okay. So that's what we mean in the beginning here, that it has to be between 1 and 10. Your first number has to be between 1 and 10. And then the second part, okay, the second part needs to be is a power of 10, and then your exponent in a superscript. Okay. After you have your times 10 with your exponent, and maybe this is where we're hung up, maybe we don't know what the exponent should be. Well, this is how we figure that out. So when we're putting a number in correct scientific notation, and specifically understanding what exponent it should get, remember Lars. If you're moving your decimal to the left, you're going to add 1 unit. You're going to add 1 for every move, every jump you make going to the left. But if you're moving to the right, you're going to be subtracting 1 unit for every jump that you're moving to the right. Okay. So another way, so when moving your decimal to the left, you add to the exponent the number of spaces moved, and then B, when moving decimal to the right, you subtract them. Okay, so let's try this out here. Okay, now I'm only going to try out maybe I'll try out because I'm a little limited on time here. Yeah, I'm very limited on time, so I'm just going to show maybe 2 of them, and then you can figure out the rest, and I can maybe post the answers to this another time. But let's just look at like this one. So what we should do is that even before this, remember, this is a whole number here, so we need to establish where the decimal is. And because it's a whole number, my decimal is going to be all the way out here. There's my decimal. Okay, there's my decimal. Okay. Now, I need to put this in correct scientific notation. So knowing that I need to have the first number be between 1 and 10, I know that my decimal needs to go here. It needs to go right here. That's my new decimal place right there. Oop, that is a bad arrow. Okay, it needs to be between the 4 and the 5. Okay. So let's try that again. Okay, so my decimal all the way out here. I'm going to take my decimal and I'm going to put it over here between the 4 and the 5. And now I'm going to just count my jumps. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. And it's 8 to the left. So because I went to the left, it's going to be a positive 8. I'm adding 8 to my just 0. Okay. So then in scientific notation, this is going to be 4.5. And let's see, let's just keep this one 4.5 times 10 to the 8th power. Boom, got it. Okay. Now we'll get in later knowing like how many of these we should keep. That's sig fig stuff, and we'll get into that down the road. But for now, I just want you to focus in on this. You need it to look like this. Single digit, dot, and then whatever comes afterwards. In this case, it's just 4.5 times 10 to the 8th power. Okay, so you would do that for numbers 1, 2, 3, and 4. But let's take a look at something like number 5. No, I said delete everything. Let's take a look at number 5 here. The bell's going to ring in just a second. So I apologize. I might have to cut this short. Okay. Or maybe I'll pick up on it. We'll see. Okay. So we've got here number 5, 2,670 times 10 to the 6th. So this one's a little easier. That's not supposed to be decimal, though that is where we're going to put a decimal. Okay. So 2,670. So again, decimal place, because the 2,670 is a whole number, decimal's all the way out here. So I'm going to take this decimal and I'm going to go 1, 2, 3. And that was 3 moves to the left. And so it's going to be 10 to the 6th power plus, or the 6th powered plus 3rd power. So then it's going to look like this, 2.6, there it is, 2.670 times 10 to the, not the 6th, and not the 3rd, but the 9th, because it's 6 plus 3. Okay, I'm going to pause it here. Oh boy. I'll pause it here, guys, and I'll pick up in just a second. It'll look instantaneous for you, but I'll pick up back up here just a second. Okay, so we took a look at that. So now let's take a look at taking a number out of scientific notation. So we looked at 2 examples of putting them in. And again, if you want me to go over that again, I can go over that again with you in person. If you need more help, I'll post the answers, whatever you need. But anyway, let's take a look at now taking numbers out of scientific notation. So we know how to put it in. For the most part, taking it out is pretty much just the opposite, more or less. So if the exponent is negative, we move the decimal to the left the same number of spaces as the number in the exponent. Okay. But if the exponent is positive, we move the decimal to the right the same number of spaces as the number in the exponent. So let's see what that looks like. So the 5.02 times 10 to the 7th. So it's a positive exponent here. Okay, it's a positive exponent. So like number 2 says, if the exponent is positive, we're going to move the decimal to the right the same number of spaces as the number of the exponent. So that just means because our exponent is 7, oops, sorry for the bell. Since our exponent is 7, we're going to be moving our decimal place here. We're going to be moving this guy 7 jumps to the right. So let's see what that looks like up here. So 5.02. I'm going to take my decimal and I'm going to go 1, 2, 3, 4, 5, 6, 7. There's my new decimal spot right there. And then I just fill in all those jumps with zeros. Okay. And then I just write down my new number, which is going to be 502.00000. I think I got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. And then we just add our commas. Boom. So 50,200,000 is our new answer. Let's take a look at another one. Let's take a look at a negative. So number 2. So we've got 9.224 times 10 to the negative fourth. Okay. So again, since number one, it is a negative exponent, we're going to move the decimal to the left, the same number of spaces as the number. So we're going to be moving 4 jumps to the left because it's a negative 4. So let's go ahead and do that. So 9.224. Take our decimal here, and we're going to move it to the left. So 1, 2, 3, 4. Ooh, a little laggy now. Yikes. So here's our new number. So now we're going to rewrite it. It's going to be 0, even though I know that's because our new guy's right there. A 0, when you've got a decimal, when you have a decimal and then there's, zeros or any decimal where you don't have a number in the one spot, you should have a 0 there. And I'll show you why just in a second. So, but it should be 0.00, that is a 0, not a 6, 0.0009224. Okay. Now, the reason why you want a 0 right here, I'll put that in red. The reason why you want this guy to be here is because if you've got a lot of numbers going on, and you want to even say put this in a calculator, if you're adding whatever it is, you want something there so that it just looks a bit more complete. Because if it looks like this, even if you're able to read this, that's fine. I know for myself, and down the road, hopefully you'll see what I see. But if you have your decimal right here, that little glob of dots there, if you see this, okay, it just doesn't look as nice. It doesn't look as complete if you don't include that 0 on the other side of the decimal. And on top of that, I've seen too many times where students do this, where they do the 0 or they'll put whatever number and they'll put a decimal right here, and it'll kind of be attached to whatever their first number is. And then so I'm left there wondering, well, is that their decimal place? Is that just an accidental pencil mark? Other students may see that. You may see that when you're doing calculations, and if you don't account for that, you may accidentally say, oh, why did I put those 3 zeros there? Oh, it's 9,224 instead of the 0.00092224, which obviously is a completely different number. So it's always to be in good practice. It's always good to do 0 and then your decimal 0.009224. And if you don't understand what I'm saying still, talk to me, chat with me, and we can go over, what I'm really talking about, how it may look down the road. Because maybe there's something we don't understand here. So, okay. And again, if you want me to go through the other examples with you, talk to me. I'll provide the answers. I'll provide the answers in the Google Classroom. They're in the description. So anyway, I'll put them there. So thank you guys. If you want to subscribe here, you can subscribe to the channel just to know when another video goes up. Because I know you're just dying for physics stuff, for physical science stuff, for chemistry stuff. So if you want to take a look at that, and know when I'm posting, go ahead and subscribe. Do what you want to do. In any case, I'll see you the next one.